Hello everyone and welcome to another video. So today I'd like to play around a little bit more with the heat equation and show how it can be simplified to yield another famous partial differential equation, namely Laplace's equation. You might recall that in a previous video we discussed how to derive the general heat equation, and in a subsequent video we looked at how to simplify it and solve the 1D heat equation. In this video I'd like to look again at simplifying the heat equation, but in another fashion here, and show how it yields Laplace's equation. I would recommend viewing both of these aforementioned videos before continuing with the lesson today. So, if all of that sounds good to you, why don't we jump over here to the whiteboard and get started. Alright, so let's see how we can get Laplace's equation from the heat equation. Okay, so if you remember, here's our heat equation that we derived earlier, right? It was partial u with respect to t is equal to c squared partial u with respect to x squared plus partial u with respect to y squared plus partial u with respect to z squared, right? So here was our full-on 3D heat equation. So let's consider a couple simplifications here. So the first thing that I'd like to look at here is, let's just look at two spatial variables. So we could think about this instead of a three-dimensional body here, you know, like a cube here. Maybe let's just instead look at this like a plate, like a flat 2D plate here. So we'll only consider x and y. And the other simplification I'd like to make here is, let's just look at steady state solutions. So in other words, I'd like to think about applying some type of boundary condition on this metal plate here, and then we're going to sit and wait a while until everything has settled out and everything stops changing. So we have a steady distribution of heat here. So what that means here is, if you think about this steady state solution long enough, what that effectively means here is that the temperature will not be changing with respect to time. In other words, du dt is going to be equal to 0, okay? So if we plug in these two simplifications into our full-on 3D heat equation, right, we see that, okay, due to the fact that we're only considering like a plate, this is gone here, right? There's no z dependence here. And finally, steady state is going to say that this is gone, right? And that's pretty much it. And we see that since this constant c is non-zero here, we could just divide through and it's basically gone as well. And with these simplifications, we see that actually the full-on 3D heat equation simplifies down to this. It basically simplifies down to partial u squared with respect to x squared plus partial u squared with respect to y squared. The other name for this here is, we can consider this maybe the 2D Laplacian of u here is equal to 0. So this is basically Laplace's equation. Okay, and we can see that this is just a second order partial differential equation. It's linear, it's homogeneous, all that kind of good stuff. So we can consider going ahead and trying to solve this. So before we jump into that, maybe we should say here that, again, this is a very famous equation. People have looked at this here with a variety of different boundary conditions. So it might be good to maybe enumerate some of the different boundary conditions that people have looked at. Well, that pen's on the way out. Okay, so there's a couple of different conditions here that are associated with the Laplace's equation and have special names here. So a Dirichlet problem, sometimes also referred to as a first boundary value problem, or BVT here. This here happens when the temperature distribution U is prescribed all around the boundary of this system here. So we can say this happens if U is prescribed on the curve C. So again, C here would be the curvature or the outside portion of this this region here. So C would be the blue here, right? Okay, so if someone specifies that, you know, there's a specific temperature distribution around the edges, you end up with a Dirichlet or a first boundary value problem condition here for Laplace's equation. You could also have what's referred to as a Neumann problem, or a second boundary value problem here. And this is if instead of specifying the temperature distribution, you specify the derivative of temperature here with respect to the normal direction. So in other words, if partial u with respect to some normal vector here is prescribed on C. So instead of specifying the actual temperature, you specify the slope effectively of the temperature at that on the edge here, right? The lastly that you one that is fairly popular here is called a Robin problem, or a third. Sometimes maybe referred to as a mixed boundary value problem here. And you obtain this situation here when u is prescribed on a portion of C, right? And where you then have the normal derivative here, or u, I guess we should say partial u, partial n on the rest. Right? So in this case, you have a mixture of a Dirichlet and a Neumann problem here. Okay? So the case I'd like to look at here for the remainder of the discussion here is, let's look at a Robin problem, or excuse me, a Dirichlet problem here on a rectangular plate. So let's go ahead and take a look at that example here. So example, a Dirichlet on a rectangular plate. Okay, so just sketch the geometry of what this is going to look like here. Let's again, we'll draw ourselves two axes here. We've got an x and a y, right? We're only dealing with two spatial variables. And the plate here, let's draw the outline of this plate here in blue here, maybe. It's a rectangle, and it's not necessarily square here. So you've got the plate runs from 0 to a, so it's a units wide by, say, b units tall here, if you want to think about it this way. So here's our region R here, right? And C is the blue contour. I guess maybe I should have drawn the blue part down here as well, right? So here's our contour C, okay? And what I'd like to do here is, let's prescribe the temperature all around this region, this plate here. So along the two sides here, let's say that u is equal to 0. And as well down here at the bottom, u is equal to 0. So this plate here is wedged into ice on three edges, right? So the ice is going to keep it perfectly at 0 degrees Celsius or whatever, right? It's just a mathematical oddity at this point, right? Just some value. But all along the top, let's say that this has some distribution of temperature. Let's call it f of x here, right? So maybe you're butted up against some heating element where, you know, one side is hot, the other side is cold, or maybe there's some triangular temperature distribution or something like that. Basically, the top edge of this plate is going to be have some varying temperature as x moves here, but the other three sides are constant here, right? So what we would like to do now is we would like to say, all right, what is the steady state distribution of temperature of this over this entire plate here, right? This now is governed by, we saw, basically Laplace's equation. So let's go ahead and solve this. And we're going to do this in actually just two steps. This is a little bit different than what we did earlier here, but really not. It's the same thing here. So again, let's go ahead and do our separation of variables. Okay, for step 1. And then step 2, we are actually going to go ahead and you see the boundary conditions are kind of interesting here, but let's just say this is just apply boundary conditions here. And we're going to see that kind of, there's no real discussion of initial conditions here, right? Because we're looking at a steady state solution. So really, we're going to see this boundary condition kind of rolls the Fourier analysis and all of that kind of stuff that we looked at in the previous two examples all into one step here. So again, let's go a little bit quickly through this because you guys have now seen this already for the 1D wave equation as well as the 1D heat equation. So this separation of variables thing should be pretty old hat at this point. I will just stop at situations where things might be a little bit different here. So, all right, separation of variables, right, for step one. Okay, so again, here let's state our our partial differential equation, right? It's partial u with respect to x squared plus partial u with respect to y squared, right, is equal to 0. So here it is. Whoopsie, sorry, I just went ahead and turned off the screen on my left. All right, so we're back. Okay, so separation of variables says, all right, let's consider that the temperature distribution, right, which is now a function of x and y only here, let's write this as the product of an x spatial variable and then a g spatial variable here, right? Okay, so go ahead, plug this into this here, and what we end up with is after you plug it in and rearrange a little bit, we basically get this thing to look like df of x dx squared times 1 over f of x is equal to negative 1 over g of y dg of y dy squared here. And maybe one quick note here. You'll notice here I switched from using partial notation here to just the plain old d term because f here, it's only a function of one variable, right? So there's no real such thing as a partial. A partial is the same thing as a derivative here. So same minor notation change here, right? Okay, so we make the same argument that we had earlier, and we say that, you know what, these things have to be equal to a separation constant k here, and this will turn into two ODEs here. So basically we end up with these two ODEs here at the end of the day. We end up with this one here of f here turns into basically d squared f of x dx squared plus our separation constant k times f of x here has got to equal 0. So here is, let's call this maybe equation A over here, or ODE 1. And then equation B here would be minus 1 over g of y. Oh, no, sorry, excuse me. The second ODE that pops out of this thing is d squared g of y dy squared, right? Minus k g of y is equal to 0 here. Okay, so here's equation B, or ODE number 2. Okay, so let's go ahead and try to solve those two. All right, so let's deal with equation A first, right? Not a big problem. If you look at this thing again here, it's pretty straightforward here. We see that again, k. This is basically an undamped oscillator again here, right? As long as k is positive here, which again I'll leave that up to you to kind of show what this needs to be. But anyway, this is an undamped oscillator here, so we end up with solutions to this right off the bat here. So we can basically say that solution is a cosine slash sine combo for this undamped oscillator. Right, so in other words, f of x, that's going to solve this differential equation here, is going to be an a cosine of square root kx plus b sine square root kx. Right? Okay, so now let's go ahead and apply our boundary conditions, namely the left side has got to be 0 and the right side has got to be 0 here, right? So, all right, next thing is apply BCs, right? So the left side, we basically said that, okay, f of 0 has got to be equal to 0, right? The temperature on the left side's got to be 0 here. So we saw that that has consequences on this f term that we've developed here. So that has got to be 0 here. So what we basically end up here with is this turns into, just plug in 0 to here. So we end up with a is equal to 0, right? That was one of our conditions here. Okay, the right side, if we do the same thing, f at x is equal to a, right? That has to be 0. So you plug this in along with our notation or our discovery here that A is 0. This thing is all gone. So we see what this pops out here is we need here that B sine square root of Ka had better equal to 0. So in order to not be trivial, we see that K actually, again, has to take on very specific values here. So what we end up out of this here is that K had better be something like n pi all over A squared with n in the integer value. So again, you've seen this probably twice already, so I'm just glossing over where this came from. I think you can probably figure this out. It's not too bad. So after all of that kind of analysis, we see that finally this f function here, the general solution here, right, is going to look something like f of x is equal to b times sine of n pi over a, right, for n in the integers, right? And again, we'll adopt this f's of n because we see you get a different solution for n equals 1, 2, 3, 4, etc., etc. Great. Box this guy up. We got our f. Let's turn our attention now to the second ODE. And I'm going to leave our picture up here because that might help us in a second. Okay, so our second ODE, right? Okay, let's deal now with equation B, right, which was our second ODE. And also, let's go ahead and make ourselves a little slight note here. We said that, all right, K is not just anything you want here, right? The K had a very specific set of values here. So in order to make everything consistent, K has better look something like n pi all over A squared, right? With n in the integers. Okay, so with that in mind here, let's go ahead and investigate that second ODE, or equation B, which unfortunately I guess I just erased. So tell you what, let's rewrite this thing real quick because I think this is useful to look at. So this is d squared g sub y dy squared minus k here, but we see here's the k values, right? So this is n pi all over A squared, right, times g of y is equal to 0, right? Okay, let's look at this again here. This is not an undamped oscillator, because if you look at this here, right, this whole thing is just some number here, right? A is like the width of the plate. So this is positive, n is positive, pi is positive. So this whole thing looks a little bit like a g prime prime minus, I don't know, 4g is equal to 0, right? It's something like this, right? Other cases like the 1D wave equation here and the 1D heat equation, this was a plus sign right here, right? And actually we just saw it over here. If this was a plus sign, right? If this looks, maybe I'll do it in another color, right? If this was g prime prime plus 4g is equal to 0, right? This here is an undamped oscillator, right? We see this thing has poles at s is equal to minus 2i and s is equal to positive 2i, right? So you had poles that were purely imaginary here, right? This case now here, the one we have, this is like s is equal to what? It's plus 2 and s is equal to minus 2. So actually, this here is an unstable system, right? It has one one positive pole, one negative pole here. So actually, the solution to this guy is not sines and cosines, right? This is actually a positive exploding exponential added to a negative decaying exponential here, right? So long story short, let me erase this little sidebar here. We see that this ODE here, this ODE, it corresponds to an unstable system. In other words, it has one positive pole. Actually, we could even add another adjective. One positive real pole and one negative real pole, right? So if this was describing a physical system like your mass spring damper, actually this is a, well, actually no, it wouldn't describe a mass spring damper because this thing blows up, right? The positive pole goes up, the negative pole goes down here, right? So in this case, we recognize here that, you know what? The solution to this system now is, something like this, right? So again, from our discussion of ordinary differential equations, we see that this is an a e to the n pi over a y plus a b times e to the negative n pi over a y, right? So here's your positive pole, here's your negative pole. These are just coefficients, and maybe, you know, what we can do is let's put n's on all, you know, on these. They're just some coefficient here, and again, we're get a different solution for each n, right? Because the n's here are integer values here, right? And I guess we can probably put an integer, like a little n subscript over here, just to again show that we get a different solution for every single different n value. Okay. So here's our general solution. So the game plan now becomes, what are an and bn to make sure that we satisfy the boundary conditions over here. So let's do that now. So let's start with the bottom boundary condition. Okay, so let's apply the boundary condition on bottom. So if you remember here, that says that, okay, the temperature at any given x and y is equal to 0, that better equal 0, right? So we see that has a restriction on g of 0, right? This had better equal 0 here, or I guess g sub n of 0 had better equal 0. Okay, so the left side here, let's plug this in. When y is equal to 0, here we have what this is. This is an plus bn has got to equal 0. In other words, an had better be the negative of bn. Okay, great. All right, let's substitute this back into our expression here, because now we know a little bit more. So let's say sub back into our g of y expression or equation here. All right, so now what we see here is we see that, all right, g of n of y, right? This has to be, you know what, I can pull out the an. Let me write it like this. An is e to the n pi over ay minus e to the n pi over ay. Oh, now where did I get the this one should have the negative sign here. Right? Something like that, right? Parentheses, parentheses, right? And actually, I'm going to get real tired of writing this e to the something minus e to the negative something here. If you remember here, your trig identities, this is actually, you know, mathematicians also got lazy here, and they defined hyperbolic sine to basically be, one half of this. Or in other words, maybe we should make a quick note here. If you recall here, if you have an e to the ay minus e to the minus ay, this is equal to 2 times the hyperbolic sine of ay, right? It's just a trig identity here. Hyperbolic sine is literally defined here as 1/2 of this difference here. Whatever. So plug this in. I just don't want to keep writing e's here. I think it might be a little bit easier to just write hyperbolic sine, but this is just purely out of laziness. You can keep writing this if you would like. But since I'm lazy and want to use the minimal amount of ink possible here on my single whiteboard here, let's just rewrite this sucker here. So this is now our gn of y is equal to 2 times an times hyperbolic sine of n pi over ay. Okay, and again, let's look at this coefficient here. 2an, it's the same thing, it's just some other arbitrary constant. So you know what, let's just rename this as an here, and I think we end up with, you know, it's just basically an times hyperbolic sine of n pi over ay. Okay, great. Okay, so this thing should now satisfy the boundary condition on the bottom, and in fact, if we compose now gn and fn, we now have something that satisfies boundary condition on the bottom as well as the left and the right side. So the last thing we got to deal with here is the top here. Now the top is interesting because the top is not a simple boundary condition, right? We need the top here to actually equal this function here, right? F of x. So this function could be something crazy here, right? It could be sines, it could be square waves, things like that. So you know what? Here's where we're going to pull out Fourier. So let's do this now. So let's go ahead and try to look at the boundary condition on top, right? And this is sort of the complex part, or at least it's more complex than what we've dealt with before. Okay, so in order to satisfy that boundary condition on the top, we are going to use our same trick we did earlier, right? And we're going to say that, okay, the total solution, it's going to be a sum of all of these eigenfunctions here, right? And I guess we should have noted here that this eigenfunction was just the Fn times Gn, right? It was those two functions we found earlier. Okay, so let's plug this in here, okay? So we end up with infinite series or infinite sum from 1 to infinity of an, wait a second, where did I come with the an star thing? Hold on a second. Oh, sorry, okay, right here. I called this thing an star. An star is just 2an. It's just, again, other arbitrary constant here, but all right, to be consistent with the notes, that's where I came with the an star here. So, okay, this is, yep, so back here to the infinite series here, we end up with this thing is, yeah, an star times, oh yeah, here, I could write it like this. Hyperbolic sine of, right, n pi over a y times sine of n pi over a x. Wait, I want to make sure I got, shoot, let me see, an sine n pi over ax, hyperbolic sine n, no, okay, I did get that right, okay. Okay, great. Okay, so here is our candidate solution here for the whole thing, right? Now, let's apply the boundary condition here at top. Apply BC at top. So in other words, I wanted to say here that my candidate solution at x, at any x, but at y is equal to b here, right? Okay, that better equal this distribution f of x here, right? That's what we're saying over here. Right? I want whatever I come up with as the steady state distribution of heat over this entire plate, along the line here of y is equal to b here, you better equal this function that is specified as the temperature distribution along the top here, right? Okay, so let's just expand this a little bit further. This left side here is basically, it's this infinite series, but when y is equal to b. So all I got to do here is replace wherever I see a y with b here, right? Let's do that over here. All right, here we are, getting there. Okay, so left-hand side is sum from n equals 1 to infinity here of an hyperbolic sine of n pi over a b here, right? Times sine of n pi over a x. Right? That's the left-hand side. This had better equal f of x. Right? Okay, and maybe let me put this in brackets here, this term here. Right? Maybe let's call this whole thing in brackets, it's just some constant, right? If you look at this long enough, right, an is just some constant, but you know, maybe we get a different a for every n. And this whole thing, this is a number, right? Pi is a number, the width is a number, the height is a number, n is a number here. So this whole thing is a number. Maybe let's call this thing like little bn here, right? So if you look at this now, what we end up with here is this has now become sum from n equals 1 to infinity of little bn times sine of n pi over ax is got to equal f of x here, right? This should be immediately obvious because we've seen this already 2 times. It's just in a slightly different form. Again, here's our Fourier series, right? With f of x expanded as an odd function, and we get here's the half-range expansion of that function, right? So here we go. All I need to do, Fourier already told me how to compute Bn here, right? The Fourier analysis said, we said that, all right, this little Bn, right, if you plug it into the Fourier expression here, this is going to be 2 over a, right, because this function f of x has a period from 0 to a, right? Okay. So this integrated from 0 to a here of f of x sine of n pi over ax dx, right? That gives me the coefficient. And what we see here is the coefficient is actually this quantity, right? So this equals an times hyperbolic sine of n pi over ab, right? What are you actually trying to solve for over here? This is what we want. It's an, right? Because if we had an, we would have, where did I, well, we basically have this, right? Because we get, sorry, did I drop the, crud. I got too excited, dropped the star notation, sorry. Dang it, I dropped it all over here, right? This is an star, or whatever, an star, right? I want an star here, right? Because the second I have that, these are the coefficients here of the eigenfunction here, right? So all I got to do is isolate this thing for an here. So this is, yeah, we're pretty much on our way. So I'll just solve for an, which basically just involves dividing through by this constant here, this hyperbolic sine of n pi over ab here, right? Send that over to the other side. So long story short, we end up with an star is equal to 2 over a times hyperbolic sine of n pi over a times b, this whole thing, right, times the integral from 0 to a of f of x sine of n pi over ax dx here, right? Perfect. So now here's how you get the coefficients, and what those get applied to here are the eigenfunction that we talked about earlier here. So our total solution, right, is just going to be the summation from n equals 1 to infinity of that coefficient that we just computed up here times sine of n pi over ax times hyperbolic sine of n pi over ay. Great, so here we go. Here's our solution to the steady state two-dimensional heat transfer equation, which we saw is actually just Laplace's equation here. So here we go. Here's how to solve basically Laplace's equation with the Dirichlet boundary conditions where the top is equal to some function and the other three sides are equal to 0. So instead of going over to Mathematica to plot this, because I think you've seen this already twice here, I'll actually, there's going to be a homework assignment looking at this here shortly. So we will take a gander at doing this actually in homework to look at how the distribution of heat over a two-dimensional surface works in this scenario. So with that, I think this is a good spot to stop here. If you like the video, again, like I said earlier, please subscribe to the channel because this really helps us continue making these videos here. The next thing in the series is we're going to actually go back to the wave equation, but look at it in 2 dimensions. And we're going to see this is where things start to get very, very interesting here. So I hope to catch you at the next video discussing the derivation of the 2-dimensional wave equation. So I'll talk to you a little bit later. Bye.